Greetings, friends and fellow humans, and maybe even potential future Martians. And welcome to Ask an Astrobiologist, the show that celebrates the science and celebrates the scientists involved in our quest to understand the nature of life. I'm your host, Graham Lau, also known online as the Professor of Everything Groovy, and we're brought to you by the NASA Astrobiology Program and SaganNet.org, which, by the way, SaganNet is now 10 years old this year. So 2021 is a big moment for SaganNet. Thanks to everyone over the years for all your support, for all the things that we've done trying to help early career scientists in astrobiology get involved in carrying astrobiology forward into the future. Now, this is our first episode of 2021, and it's got some red planet awesomeness that I think we're all really excited to talk about. In case you didn't know, within the next 3 weeks, we have 3 missions arriving at Mars. The HOPE mission from the UAE is arriving in orbit here on the 9th. On the 10th of February, Tianwen-1 will be arriving at Mars as well, and has a rover that we're looking at a May touchdown on Mars. And then, maybe most importantly for many of us, Percy, or NASA's Perseverance rover, is scheduled to land on Mars on the 18th of this month. And so we have a very special panel episode to talk about Mars astrobiology, about curiosity, about perseverance and ingenuity, about the instruments and all the science that's going into this landing and all the research ahead, sample return, and all these other awesome things. But before we get there, as many of you know, we have our Ambassador of the Month to announce. Every single month, we like to point out the people who've done the most work on Twitter and other social media platforms and email and websites to share information about our show and get the word out there. And this month, we'd like to point out 4 users from Twitter who did a great job sharing information about the show, helping us to advertise, and just showing some Ask an Astrobiologist love. These are users at Space Nassim, at Azul Pinoba, and at Strayologists, and at Just Grelda. All longtime watchers, observers of our show. And now Space Nassim, whose real name is Mariam Nassim, is also now helping in the background along with Sarah Treadwell. I also want to give a huge shout out to Mike Toyon, our producer and director, and Sanjoy Som for helping us run this show and keep things lively. Now, without any further ado, let's bring in our guest for this very special panel episode. First off, we have Francis Rivera Hernandez. Dr. Rivera Hernandez is a planetary geologist who very recently transitioned from a postdoctoral position at Dartmouth College into now becoming an assistant professor at Georgia Tech. Dr. Rivera Hernandez uses a mixture of field research, remote sensing, and numerical analyses to reconstruct paleo environments, interpreting things like paleoclimate and paleohydrology and the habitability of planetary bodies. So Francis, hi, and thank you. Welcome to Ask an Astrobiologist.
Thank you, Graham. Excited to be here and nerdy about Mars.
Paleoclimate, paleohydrology, paleoenvironments, there's lots of things that you're learning about the past. Could you quickly give like a synopsis of the kind of research that you do for our audience?
Yeah, sure. So a lot of my work, as you alluded to, is focused on characterizing the surfaces of planetary bodies, specifically Mars. And for that, I use a lot of data from the Curiosity rover and really trying to use the rock record to reconstruct what past environments or paleo environments were present on Mars in the past. And I also do a lot of field work on Earth in analog environments, so environments that we think might be similar to those that were present on Mars to better interpret the data that we get from missions. And so that's, I guess, essentially what I do. And again, excited to be here.
Awesome. It's great to have you. And we're going to talk a lot about Mars environments and analog environments here on Earth with all 3 of you. Our next guest is Dr. Kenda Lynch. Dr. Lynch is an astrobiologist and geomicrobiologist. She's worked as a systems engineer for the International Space Station program and as a research engineer for the Astromaterials Exploration Science Directorate, both of which are at NASA's Johnson Space Center. Dr. Lynch currently studies life in extreme places on Earth in these analog environments as models for characterizing habitable environments and searching for life on other planetary bodies. Kenda, welcome. Thanks for joining us, and welcome to Ask an Astrobiologist.
Thank you. It's so great to be here. I'm really excited to be on the show, especially with Francis and and our next guest, Vet. It's just an honor to be here.
I'm so glad to have you. And we've known each other for a very long time now, you and I, since back in our earliest days here in Colorado, quite long ago. But one thing I never really had a chance to chat with you about was this transition in your career from engineering kind of focused work into more of the geomicrobiology, the geology work. Could you speak to our audience a little bit about that pathway of engineering into geology?
Sure. So I started out in human spaceflight, and I really liked what I was doing. I was working on developing human habitation systems for space station, and eventually working on things for future human spaceflight. But I'd always really enjoyed the fusion between engineering and science, and especially using my biological skills. And I learned about astrobiology and this whole area of astrobiotechnology, and using our advances in biotechnology to help us do more research for looking for life in the universe. And I just got very impassioned about that. And an opportunity came up at Johnson Space Center to work with the now deceased David McKay, who's one of our senior, astrobiologists and well known in the field. And I took it, and they convinced me to go back to grad school. I got to spend about 4 years working at Johnson Space Center, developing technologies to help us improve our abilities to look for life on other planets. And then I just got really interested in the science side of it, and then decided to go back to grad school to kind of focus on that. So it was a really fun transition. I still sometimes get to put my engineering hat on when we develop instruments, both here at LPI and with other collaborators. So it's kind of fun to be able to wear both hats now.
And that's awesome. I think you had a little pause there, but that's okay. We just lost you at the very end. It's so good to have you here, Kenda. And we're going to talk a lot about your careers. I imagine we'll have questions from our audience who are watching right now on seganet.org and the NASA Astrobiology Facebook page. Those questions will come through the teleprompter to me for later. And I'm sure we'll have some about your careers as well. And then our third guest on the panel today is Dr. Svetlana Shkolyar. Svet and I have also known each other for quite some time, and I've known her both as a researcher and as a communicator of science. Dr. Shkolyar is currently a postdoctoral fellow at NASA's Goddard Space Flight Center, and she works on life detection techniques for planetary surfaces using laser spectroscopy. Her work also involves studies informing the sample caching system and sample return for the Perseverance rover. Svet is also passionate about SciComm, sharing science, empowering the next generation of planetary explorers. So Svet, welcome to Ask an Astrobiologist, and thank you.
Thank you, Graham. It is an honor to be here with some of my favorite people.
Yeah, I mean, you and I have also known each other for quite some time. You've also done a lot of work in science education and science communication through SegaNet. I wonder for our audience if you can just speak briefly about the importance of not just doing science, but also of sharing science.
Yeah, absolutely. I mean, it's such a privilege to be doing this kind of science. And I just feel like our job is not complete if we don't, excite the public about it. And within the field of astrobiology, it's just such an engrossing narrative, for life out there. I feel we all, since the time we're kids, we're all excited about this topic, and just being able to excite people about that every opportunity I can, I think is just one of my favorite parts of the job, honestly.
Awesome. Yeah. When you're in love, you have to tell the world, right? So we had a lot of love for this episode on Twitter and Facebook and Instagram and LinkedIn, all over the place. I heard a lot of people talking about it. There was a lot of buzz. And the NASA Astrobio at NASA Astrobio account on Twitter shared some polls, some questions for their very large audience on Twitter about the upcoming mission to Mars with Perseverance and upcoming Mars research. One question that we asked people, so that Perseverance looks a lot like Curiosity. They have the same chassis. They're very similar looking. But we asked the audience if they know what makes the missions different. And we had a few answers we wanted to point out. Anirudh Mohante, who is at Strayologist, said that Perseverance is going to collect samples and drop them so they can be brought back to Earth through a sample return mission. And that's true. That's a very big thing, is sample return from Mars. I think a lot of us want to talk about that. Camille, who goes by @kilo_Mora, said that she can't wait to see Ingenuity fly and listen to the winds of Mars. And I agree. Putting a microphone on Mars and listening to the sound engaging with it in a human way and flying a drone around is going to be cool. And then user at JustGrelda said Curiosity is a great rover, but it isn't an astrobiologist like Perseverance. Perseverance will look for signs of ancient life or modern life on Mars, and that's true. Perseverance is an astrobiologist robot, and that's pretty cool for all of us to talk about. So, Francis, I wanted to bring a question to you because of this. You worked on Curiosity. What do you think were the successes of the Curiosity mission? What we learned from that mission, and how will Perseverance build on those successes?
Yeah, so Curiosity landed back in 2012, and it's still an active mission. So I would say that it has a lot of successes. However, I think one of the main successes has been actually achieving the main goal of the mission, which was to identify and characterize habitable environments on Mars, in particular in Gale Crater. And we've done this by identifying deposits of rivers, which provide evidence for running liquid water, and also the deposits of lakes, which provide evidence for sustained liquid water. And lakes in particular are important because they are possibly stable water environments where life could have persisted or evolved on Mars's surface. And with Curiosity, we know that some of these lakes could have been present on Mars for tens of thousands to millions of years. And so with Perseverance, we're taking this a little step further. Instead of only characterizing and identifying habitable environments, we're asking the next obvious question, which is, was there actual microbial life on Mars in the past? And so all of the instruments on Perseverance were selected specifically to answer that question. And with that, which you alluded to recently, is the sample return part of the mission, which will core rocks that we think might have biosignatures, so this evidence for past life in the form of fossilized cells and organics, and hopefully storing that for a future mission to return. And then I also wanted to say, also from an engineering side, since the landing's going to be happening soon, that one of the novel things with Curiosity was the landing system, which we call the Sky Crane, which consisted of a platform that hovered over the surface and slowly lowered the rover onto the ground. And so with Perseverance, we're going to be using a similar technique, but it's updated. And so it will be using an automated system to be able to detect hazards and land the rovers safely. And so from an engineering perspective, we'll be advancing some of the successes that we've had with Curiosity, among other things that are novel with Perseverance compared with Curiosity. But I'm assuming we'll be talking more about that throughout the episode.
Yeah, we'll definitely talk about all the instruments and things on board.
Yeah.
And I really hadn't thought much about changes in the Sky Crane system. I will admit, I was one of those naysayers who was naysaying before Curiosity went to Mars. I was really worried the Sky Crane wasn't going to work. It was an amazing feat of engineering for Curiosity, and it will be for Perseverance as well. And so I hope everyone, when they're watching the landing, understands that during that period of silence when the rover is landing, that's a really important time, that a lot of lines of code are running through that system to make that landing system actually function correctly. It's a beautiful feat of engineering. So we had another question on Twitter as well. We asked people, Percy is heading to Jezero Crater. And as Francis just alluded, we're looking for signs of life, past or present life using this rover. And so we asked people, why Jezero Crater? And so we had a few people who pointed out that there are dry lake basins with high potential for preserving signatures of life, biosignatures. So 4 of our winners from this competition we wanted to highlight are at SpaceFia, at Naharika Hopade, at Endless_Forms, and at Eduardo Aco 1. So thank you very much for everyone who answered that question on the at NASA Astrobio Twitter account. It's always great to see all of you interacting, and those of you who really know what's going on right now with this landing site. And my next question then, Kenda, since I know that you were involved in landing site selection and the workshops, and you know a lot about Jezero Crater, I was wondering if you could tell our audience really why Jezero was selected as the landing site for Perseverance.
Absolutely. So, as Frances said, one of the things that we looked at and we've really been able to learn about even more from curiosity in a lot of our orbital investigations is we've been able to see and find and characterize places where we have physical signs that liquid water either flowed or was sustained. And with Jezero, we have both. We have this beautiful crater that has this gorgeous delta system that told us that water flowed from the channel into this beautiful Paleolake basin and was stayed for a long enough period of time to make this beautiful delta deposit and the Lake Fleur deposit, of which some of it we can access, some of it we really can't access. And what makes Jezero so wonderful is because we have that deltaic deposit that tells us that we both had water flowing and sustaining the lake, we have a multitude of potential habitable environments that we can look for biosignatures from. We have environments within the lake itself, and we have access to potential preserved biosignatures from environments that were maybe upstream from the lake and were flowed in and dropped into the lake bed and then were preserved there. So we have just a whole beautiful host of potential places where we could get biosignatures from. So the key ones in the lake themselves, there are two key places that we really want to look in the lake themselves for biosignatures that could have been formed, maybe even potentially in the lake. One of them, the big one that a lot of the scientists are excited about, are these, what they're calling these marginal carbonates. And it's another reason that Jezero crater is so amazing. Kind of up on the delta rim and on the rim of the crater, we have this huge area of actual where we actually detected magnesium carbonates. And this is amazing because carbonates are hard to detect, and we're seeing it. And because we're seeing it, that means there's a lot of it there. And usually on Earth, when we see these kind of things like in lakes and in or even on kind of like in coastal areas, they tend to be places that harbor what we call microbialites. And these are actual carbonate sedimentary structures that are made by and inhabited by microorganisms. And especially in lake environments on Earth that are very, very salty, hypersaline lakes like the Great Salt Lake, which is right next to my field environment, we see these kind of microbialites right on the lake shores all the time. And so scientists are really excited that what we're seeing may be remnants of microbialites that grew in the Jezero Crater Paleolake system when there was still water there. So that's one of the biggest sites we're the most excited about. The other site that we're excited about is the deltaic bottom set deposits. These are these really fine-grained deposits that are like the last things basically to drop out of the water that is entering the lake from the channel system that is basically feeding it. So these sediments are the last things to drop out, and they're really fine, and they're really tiny, and they're really good at, one, binding to organics, and two, preserving organics. So we're really interested in that site because that is a great place where any kind of biosignature, any kind of organic biosignature that maybe had come from a habitable environment that was upstream of the lake and got captured or dumped into the flowing water and then flowed into the lake, it could have been trapped there, bound there, and stored there for the many millions of years it's been sitting in those lake bed deposits. So we're very excited to look at those deposits as well. So those are two of the big places that we're really excited to look for biosignatures in Jezero. And there's some other possible places on the Delta Plain where we could have had spring deposits. There's just so much diversity in Jezero for possible habitable environments. Then that's why we really are excited to get there and to get Percy on the ground and get her started looking.
That's so groovy. Yeah, and for all those watching, I mean, we always have multiple potential landing sites that we're looking at. There are lots of really cool places on Mars to explore. Jezero won because of these interesting features. And so I think a lot of us are excited for Percy to get going inside of Jezero Crater. And there's a lot of exciting things about this mission. Svet, I wanted to bring you in next then and just tell us what excites you the most about this mission, and maybe even for the future of Mars exploration because of this mission.
Yeah, well, we know that the Perseverance rover kind of on the surface looks a lot like Curiosity, right? The skeleton, and it seems like, oh, what's new, what's special? But really, Perseverance rover represents the first step of Mars sample return. I mean, this is something that we in the astrobiology community have been waiting for a long time and preparing for a long time. this mission is not only going to understand the habitable environments in Jezero where it will search for signs of life, but it is also intended to cache samples. It's intended to find samples that may actually preserve ancient signs of life, study those samples in detail, do a ton of documentation, and if the science team determines that, yes, this could be a potential signature of life, a potential biosignature, then that rock is going to be cored and cached into a container that is going to be sealed very, very tightly, what we call hermetically, and stored in this very complex system. It's going to have this carousel, and then it's going to be, the sample is going to be imaged, and then it's going to be stored in this sample caching system. And then another sample fetch rover is going to come back in the future, pick up those samples, and eventually potentially bring them back to Earth. That is the campaign that we call the Mars Sample Return Campaign. And in order for us to really do good astrobiology, we want to have those samples back on Earth. We want to have those cached samples so we can study them in the high resolution laboratories here on Earth. And Perseverance really represents the first step of that 3-part campaign. So I'm just really excited to see what kind of samples we come across and cache, and maybe a decade from now. It's said that as early as the early 2030s, we may be able to get the samples back, maybe a little bit later. So, in our lifetimes, we will see those samples return to Earth for study of potential signs of life with high resolution equipment here on Earth.
Yeah, I really hope so. For myself, I've done a bunch of research using synchrotrons, these large particle accelerators. And I remember when I was working on them, I'm like, I can't take a giant synchrotron to Mars, but we can bring samples back and we can look at it that way. So I think a lot of us are super hopeful for bringing those samples back. And then we also have a lot of really cool instruments that are going to be on Percy. So another poll question we put out through the @NASA Astrobio Twitter account, we said there's a bunch of incredible instruments, but maybe of Pixel, RIMFAX, SHERLOC, and SuperCam, what's your favorite astrobiology instrument? And we had over 614 votes on that tweet. And SHERLOC won with about 39% votes. SHERLOC is going to be a Raman spectrometer, which I'm very excited about. I know Svet is as well, since she has a lot of experience in Raman. And I think many of us in the geo community are super excited about having Raman spectrometers going to Mars now as well. And so this kind of brought to mind for me just a really quick rapid fire question for each of you. Is maybe what is your favorite instrument and why? In like one simple sentence, say you were talking to a high school student and you had to explain in one sentence why that instrument is awesome. What would it be? So Frances, I think we'll start with you.
So seeing as I'm part of the CamCam team, which is on the Curiosity rover, I would have to say that SuperCam is my favorite instrument. It's like, come on, it has lasers that we can use to zap rocks on another planet. And of course, it's going to have a microphone, which you also talked about earlier, which will give us the ability to listen to the sounds of Mars for the first time. And so, that to me is my favorite instrument.
That is pretty cool. And I love the pictures we have from Curiosity of like lasers popping out and cats jumping off the surface of Mars. I imagine we're going to have those as well for Percy. Kenda, how about you? What's your favorite instrument or an awesome instrument? And maybe in like one simple sentence, why?
Well, I do love SHERLOC. I'm so excited with SHERLOC, but I have to admit that one of my favorite instruments that I'm really excited about too is Pixel, because Pixel is going to let us do things as a geomicrobiologist. I'm so excited that that's something I do in the lab a lot to look at the structure of my samples that I take from my environment. I'll be able to do on Mars, and that Pixel will let us not only take pictures and look at tiny little structures, but it's all it actually can map, literally pixel by pixel, all the different elements. And so we can take a point map of all these different elements, which gives us so much information if there are biosignatures there. So I'm going to be really excited to see the pretty element maps that we're going to get back from Pixel, because can give us so much information about what biosignatures can be there.
I'm so excited too. I love element maps. They're so beautiful. How about Svet? What's your favorite instrument and maybe like one simple sentence why?
I'm going to have to agree with the poll results. Definitely Sherlock all the way. This is an instrument where you get kind of a 2-for-1. You not only get the Raman spectral fingerprint, but you also get a fluorescence fingerprint, which gives you a different level of fingerprinting of the same structure. So you get a 2-for-1 spectral structure about organics in a sample. And Sherlock is said to be as sensitive as parts per million. So that is pretty amazing resolution that we're going to get on tiny microscopic structures. And if we couple the Sherlock maps with pixel maps, that I would say is actually going to be way cooler.
Awesome. So you guys heard it. So we have SuperCam, Pixel, and Sherlock are kind of at the top of our list here as astrobiologists. Even though I'm also really excited for Ingenuity. It's going to be a very simple test of a drone, but it will be the first drone we're going to try to launch off of a rover on Mars. So that should be very cool as well. So before I go on any further, I do want to remind our audience watching, you can still ask questions for our panelists in the chats on SaganNet.org or in the NASA Astrobiology Facebook chat or on Twitter using hashtag AskAstrobio. I promise I will open it up to your questions soon, and I'll try to get to as many as we can. But first, I have one more question for each of you directly. Francis, a lot of your work is focused on paleo environments and past surface environments here on Earth and in planetary science for other worlds like Mars. So what are the current big issues in understanding the past history of Mars? And how will missions like HOPE and Tianwen-1, and especially Perseverance, how will they help us learn more and uncover some of these mysteries about Mars's past history?
Yeah, so in addition to this big question that we're trying to answer with Perseverance, right, which is, was there actual microbial life on Mars in the past? The two main questions that we really have about Mars concerns its climate and its water history. And the reason that we're asking these questions is because Mars today is cold and dry with a really thin atmosphere, and liquid water is not geologically stable on the surface of Mars today. However, as we've been talking about, there's abundant evidence for the presence of liquid water on the surface of Mars in the past. And so this suggests to us that the climate of Mars must have been different in the past than today to be able to sustain those water environments. And so we really want to truly understand what was the climate of Mars, how has it changed through time, and then also with that, the water history. So how much liquid water was present on the surface of Mars in the past? How was it distributed on the surface? And then when during Mars's history did we have these water events? And so with the new missions, well, with Curiosity, we're currently exploring some of these questions. But with the new missions, as you mentioned, we have Perseverance, and then also the Tianwen-1 missions. And both of those, of course, are rovers. And so we'll be able to characterize the physical characteristics and the chemical characteristics of the surface of Mars to try to interpret these paleo environments from the rock record, so these past environments. And that will give us information about what Mars was like in the past. And then with Tianwen-1, it also has an orbiter. And so with that, it'll be able to take color images of the surface of Mars. And so hopefully it'll give a more regional perspective of the geology of Mars and then tie it with their rover results. And then with the HOPE mission, that's specifically going to be looking at characterizing the atmosphere of Mars, specifically the upper atmosphere, and trying to constrain how much hydrogen and oxygen is being lost currently on Mars, and then also trying to understand how different parts of Mars's atmosphere interacts with each other. And so with that, we might get a better understanding of not only what Mars's atmosphere is today, but also how it was like in the past. And so with all of these missions, as I've just said, these are all different, and they're all going to have different instruments, but they're all going to be working together to try to answer some of these big questions that we have about Mars's climate and its water history and how it's changed through time. And so I'm really excited. It's a good time to be a Martian and have all these missions working at the same time.
Yeah, that is very cool.
Yeah.
It's just so cool to think about, like the synergy, like you mentioned, of these different robot explorers who are doing all this science, with us and for us at Mars. And this is something that's really near and dear to my heart, are analog systems. And we've mentioned this a couple of times already. Earlier, you mentioned the Great Salt Lake and your field site near there. You've also recently been featured in the Netflix documentary Alien Worlds, doing some work in the Danakil Depression in Ethiopia. I wonder if you can tell our audience about these analog sites and why we use them as test beds for Mars and what we're learning from all these extreme environments on Earth.
Certainly. So, so my other field site in Utah is the Great Salt Lake Desert, which is a Paleo Lake Basin, like Jezero Crater. And then the Danakil Depression is another amazing area where we have things like we have Paleo Lake Basins and we have playas, and we also have this great, amazing hydrothermal system, the Dalal hydrothermal system, that is unique because it is a poly-extreme environment. It is super hot. It's super acidic, pHs 2 or below. I've measured down to 1, and also extremely salty. Like all of the terrace features that you saw in that Netflix episode, those were all salt. But then also lots of iron and lots of sulfur, because there's a lot of salt. The salt in the subsurface gets mixed with the iron and sulfur and gets brought to the surface. So the reason we like to use these analog environments is because they're analogous to Mars in kind of their makeup and their geological makeup, the similar minerals, kind of similar minerals and similar environments that we think we had on Mars. But on Earth, we don't even understand them ourselves. So we try to understand these environments and try to understand the microbes that live in them. And once we can start to understand them, then we can try to use that information to translate how we can look for that kind of environment on Mars. Like, for example, at Dalal, the thought of a poly-extreme salt hydrothermal system on Mars never came to my mind until I went to Dalal and was like, this could exist on Mars. Oh my gosh. So how do we go about looking for that? So how do we go about looking for remnants of a super acidic, super salty iron and sulfur salt hydrothermal system? Well, we need to characterize the system on Earth so we know what kind of minerals are there, what do the mineral mixes look like, what do they look like to Mars-like instruments, what would they look like, if we send a rover there? And then the question is, if it's a habitable environment, which we're exploring Dalal, and we've got different evidence that, there's kind of a big debate about the evidence of the life there. We've got those of us that have found life, and then there's those that haven't found it. So, we're being scientists and arguing about that. But we're trying to understand if life can live there, how can it live there? And what kind of biosignatures would it leave? So that's why these environments are so important, because we have a data set of one to compare against when we go to look for life on another planet. So it is the veritable needle in a haystack. What we just try to do with looking at life on Earth and trying to understand similar environments is we try to organize the haystack a little bit better so we can find the needle a little easier. But it's still a very big problem. But analog environments help us at least give us a kind of a little bit of a direction in with which to go and to try to find evidence for life on another planet. So it's really important and really helpful. And it helps us understand how life came to be here on Earth and how diverse life is on Earth, because we still don't fully understand how life came to be here and how it was just so pervasive on Earth. So it's a really great opportunity to both learn about our own planet and our origins, and to help us develop better tools to look for life on other planets.
Yeah, so a few things that you pointed out there that I really appreciate. One, there's always going to be debate in the sciences. I love that you point out that is there life, is there not life, and there's an active debate there. Just like right now with the phosphine potential detection on Venus, there's been active debate in the literature from scientists on both sides trying to figure out if that was a real detection or not, and if it is, what does it mean? And this happens a lot in the sciences in various ways. And I'm really glad, too, that you brought up, the importance of understanding life on Earth. We don't have everything solved. And so a lot of times for us astrobiologists, people right away want to talk about aliens and other worlds. And we almost instantly kind of just skim past the thing that we really don't understand is life here on Earth. Where did it come from? How did we start here on Earth? And how have we evolved through time? We've learned so much, but there's still a lot more to learn. Svet, I see you joining us again. I'm glad you're able to reconnect. So I do have a question for you involving spectroscopy. You mentioned earlier that Sherlock is not just Raman, but it's also fluorescence. And you've done a bunch of work in the realm of spectroscopy that's relevant to Percy. I'm wondering if you can talk a bit for our very general audience about what spectroscopy is and why this is so important for Mars astrobiology.
Yeah. A lot of people are familiar with Raman spectroscopy. This is basically a way to fingerprint a molecular or a mineral structure. You're basically bouncing laser light off the surface of your sample, and that is telling you something about the vibrational structure of that sample, the way that light interacts with that sample and bounces back off. And fluorescence spectroscopy is kind of its lesser known cousin, but I would say a very powerful complementary technique to Raman. Fluorescence gives you an absorption and a re-emission of that energy. So you're probing a slightly different part of that same structure, and you're getting two different types of spectral fingerprints with one spectrometer, basically. That's why I called it a 2-for-1. And the really interesting thing about SHERLOC as well as SuperCam on the Perseverance rover is that they're both combined Raman and fluorescence systems, and this is the first time we've ever put a laser Raman and a laser fluorescence spectroscopy system on the surface. We're about to put this on the surface of another planet for the first time. This is the first time they're flying ever. And on Perseverance rover, we're getting not one, but two of those systems on the same rover. And the differences there are a lot of differences between the two instruments, of course. SuperCam is more of a distance technique. We're going to be able to scout out rock sort of in the distance and say, yeah, that's the one that I want to do more close-up analyses on. And SHERLOC is really going to be a contact instrument where you're going to be able to get, millimeter or even micro scales that are like the width of a human hair, basically. So you're really going to be able to see a lot higher resolution with the SHERLOC instrument. And so I'm excited because I've worked with these instruments since graduate school, and this is finally we're going to see them in flight, in use, in action. And also I think that they're very, very powerful instruments to be able to probe a sample non-destructively. We've sent organic instruments to, for example, on Curiosity rover, we've got the SAM instrument, and that is a very powerful wet chemistry lab. But the advantage of Raman spectroscopy is we don't have to powder those samples. We don't have to destroy that surrounding context, which we in astrobiology really, really, we love our context. We want to know what is surrounding that organic structure or that potential biosignature without degrading the rest of that rock matrix. And so laser spectroscopy represents one very powerful and high resolution technique to get this type of data. And on the Perseverance rover, the strategy sort of to use spectroscopy as kind of a first step to find potential biosignatures, and then continue to characterize those targets with the rest of the very powerful instrumentation, with the Pixel, with the other, with the imagers. And if those samples are cached, and then if they come back to Earth, we'll sort of have an end-to-end analysis on those samples, where we start with a non-destructive, non-abrasive technique like Raman. We target exactly where in that rock core we want to look for a biosignature, this region with this preserved little potentially organic structure. And then back on Earth, we can relocate that same structure and then continue to do more destructive analyses and more higher resolution analyses, like Graham mentioned, synchrotron and additional types of analyses back on Earth. So I think this spectroscopy represents a very powerful first step in this end-to-end way of looking for biosignatures. And this is the way we would do it on Earth. If we were looking for biosignatures on Earth, we'd probably start with something like a non-destructive spectroscopy type analysis, fingerprint the regions we're looking for, and then build on the level of higher resolution and additional layers of data as we progress through our analysis.
I love that. And as you were speaking, two things that came to mind for me were scale and context. Being a geologist, but also a biologist and having a background in astrophysics, scale is a huge thing. We have different scales of remote sensing in these instruments and different levels at which they can probe into the sample and bringing samples back and getting even finer scale measurements, but then also understanding the context, the history, the things going on geologically around it. What is the environment? These are all so important for us. I could honestly nerd out with all three of you for like ever just talking about the astrobiology of Mars and beyond. But we are running out of time a little bit here. And so I really want to open it up to the audience questions. I have been informed we're actually getting a lot of questions. And so if you wouldn't mind just being a little brief, if you can, when you answer, and any of you can answer these questions, I will ask some directly to a few of you. The first question we have is from Romil Kinger on Twitter. Romil asks, how will Perseverance help in finding the origin of methane and its seasonal fluctuations as seen on Mars by Curiosity?
I think the answer is that's a good question. The origin of methane is a big question that the whole community is one of our biggest arguments right now is where's that methane coming from? So I think that's a good question. I'm not 100% sure we can fully determine the origin of that methane with Curiosity. With Perseverance. I think we need some other orbital measurements, and we probably also need a mission to kind of some of our icier areas also to kind of help us understand kind of what's maybe going on with the methane. So it's a very good question that I'll tell you right now that the science community is definitely still kind of pondering and arguing about.
Yeah, and the things like the Trace Gas Orbiter and other orbiting instruments can help us look for methane and perhaps its sources on Mars, but there's a lot to learn there, so thank you. So we talked a bit about analog environments. Kenda mentioned a few that she studied. Francis, Carl L.R. Lang on SegaNet wanted to know which analog environments you mentioned earlier.
Yeah, so one of the main environments that I'm really interested in are ice-covered lakes, and so for a lot of my PhD, I studied lakes that are permanently ice-covered in Antarctica. And as we've mentioned, we found evidence for lakes on Mars, and commonly a lot of people assume that because we have lakes on Mars, that Mars's climate must have been warm. But in Antarctica, we have all of these lakes that have, some of them 100 meters of liquid water. Like the liquid water columns can be, up to 100 meters deep. And the mean annual temperature is below zero. And so a lot of my work has been focused on trying to determine if we can identify the difference between paleolakes and the rock record. And that's an example. I also study alluvial fans in the Arctic, which is another type of geologic feature that need water to form. And they're all over Mars. And so they're one of the best evidence that we have that Mars had liquid water. And so I'm trying to figure out better ways to determine in what environments those alluvial fans formed. And that's the succinct version to keep going.
Awesome. Yeah, alluvial fans are so cool to see in more barren environments like in the Arctic where you can actually see just like these really beautiful features. Our next question comes from Facebook from user Priyabrata Das. Priyabrata wants to know, so if there was an ocean on Mars, can we expect to find any traces of that ocean by exploring Jezero Crater?
So I could take a stab at this. Of course, as Kenda mentioned, there's this beautiful deltaic deposit or deltaic landform in Jezero Crater. There are actually other deltas in Jezero Crater. That's just the biggest one and the one that's going to be targeted with Perseverance. And the Jezero, and so that of course gives us evidence that there was sustained water in Jezero. But one thing that we haven't talked about is that there's a channel on the other side of the crater, which makes this what we call sort of an open crater. And so it's an outflow channel. And a lot of people do think that it's possible that that outflow channel was connected to a larger ocean in the northern hemisphere of Mars. And so it is possible that some of the geologic evidence that we see in Jezero Crater, particularly thinking about how lake deposits came and went, right? Thinking about if it's shallow or deep, and looking at salts, like Kenda was suggesting, that we might be able to connect what we're seeing with Jezero with this possible northern ocean. And we have evidence for that from other delta deposits across Mars. And so that's sort of a way that we might be able to address that question. Maybe not directly, but sort of indirectly.
It's awesome. Yeah, it's just having that synergy of studying some things in Jezero that could connect to future studies as well of this northern region of Mars. Svet, this next one might be for you. This is from SegaNet, from user Andrew R. Bowman. Andrew wants to know how the precious rock samples collected on the Mars mission and brought back from sample return, how they might be distributed amongst the community in astrobiology and in science. Do you know, do we even have a plan yet for that, or is that just so far away that we're not even quite there yet?
We're in the very, very early stages of developing that plan. So not a lot is known about that. Facilities will need to be built for that to actually happen as well. So depending on a lot of political questions and a lot of questions about contamination protocols and, for example, previous countries that have already had the ability to collect extraterrestrial samples like meteorites, and countries that are familiar, like Japan, with analyzing things like solar dust samples. They'll probably be at the front of that line, but that is a great question, and yeah, it's still in process. The answer to that question.
I can also follow up.
What's the answer too?
Yeah, I can follow up a little bit on that as well. Now that I recently joined the steering committee for the Mars Exploration Program Assessment Group, and we just had a recent virtual meeting where it was announced that the Mars Sample Return Program Office, that structure, NASA has put that structure in place. So we actually have now a focused program office whose whole job is to focus on sample return, and we do have an international team. First, we have sample return scientists that were selected for the Mars 2020 mission, and their whole purpose to be part of the Mars 2020 mission team is to help us choose the best samples that will get returned. We now have another committee that got selected from both U.S. participants and internationally, that they're working on, okay, once we have, how are we going to get these samples returned? How are we going to manage them? What do we need to do to manage them? What do we need to do to partition them? So there is a committee in place. There are people working on, as Vet said, there are a lot of politics behind it that we have to figure out, and a lot of logistics, but we are pretty set in this course. NASA has committed the resources and the Mars Sample Return Program Office to make sample return happen, and we've gotten international cooperation from our international scientists in the science community and other space organizations to basically participate in sample return. So there are a lot of questions to be answered over the next few years, but we are on our way to answering those questions.
I love it. It reminds me of the old song from World War I. I don't know where I'm going, but I'm on my way. That Carl Sagan famously loved to quote over and over again. Kenda, this next question might also be for you. We have Elise Harrington, who's user at Illusium on Twitter. Very cool name, Elise. Elise wonders, so Jezero is famous for its beautiful deltaic deposits. However, on Earth, deltas can be stressful places for organisms because they're places where different water bodies are mixing. How do we know what the water chemistry flux near Percy's landing site, how it might have changed through time?
That is a very good question that maybe you and Frances can help, because she does more paleoconstruction work than I do. But I mean, a lot of it is just basically being able to study the mineralogy of the rocks, and in particular, if we can get a good view of the outcrop of the delta, then we can start to get a good understanding of the different water sequences. Because especially at a lake environment, the water chemistry can change over time. But the beautiful thing about the lake environment is it's a sedimentary environment, and sedimentary rock is very good at capturing and preserving also what the water chemistry was in time, and we can actually kind of figure that out. So if we get lucky like we did in the Mars exploration rovers and drop right into a pretty exposed outcrop, I don't know if we'll get that lucky, but we should be able to drive up to a nice outcrop and look at the sedimentary sequence. Then we'll be able to kind of actually survey that mineralogy and help us understand how the water chemistry changed. Another great thing about Jezero that I want to make sure to let you know about is not only do we have an opportunity to study and look for biosignatures of life that could have existed in the actual open lake. But when that lake water went away, we're now starting to learn that groundwater was a big issue. And so it's quite possible that when the lake water went away, there was a lot of groundwater moving through those sediments that could have supported microbial life. And so also studying these sediments, we might be able to get an understanding of how much groundwater had an influence on those sediments, and therefore also could have supported basically a shallow subsurface ecosystem after the main lake went away. So we have a lot of things that we'll be able to learn once we can get up to that rock and take a really good look at those exposed outcrops. And if I missed anything, Francis, please jump in.
I love it so much. Actually, Francis, if I can, I'd like you to answer that question as well as our next one at the same time, if you don't mind, because Ricardo Cabrera is also interested in Jezero. Ricardo wants to know what the source of water could be as well that filled Jezero. Could it have been rain falling from mountains, or was there another source for water in the ancient history of Mars? If you wouldn't mind speaking to both of those things.
Yeah, sure. So I thought that Kenda did a great job answering that question. The only thing I would add is that the watershed for the Jezero Crater Delta, so the other tributaries and the other parts of the stream that feed into that main river channel also are sourcing other environments. And so all of those channels are also might potentially be transporting signals for biosignatures from other locations and then being deposited in the actual delta and in the crater lake itself. And so that's another reason that we went to Jezero and why we think this is a good place, because in addition to both of the things that Kenda mentioned, we have an opportunity to trap information from all of the upland regions. And so it's kind of like a trash can, right? It's just like grab all for everything. As far as the water, that's a very good question. That's one of the things that I was alluding to, that we still don't have a good handle for what the source of water was on early Mars. A common, and I think the most popular theory is that potentially snow accumulated in topographic highs, and then the snow melted, allowing, giving a source for running liquid water. There's also a lot of evidence for groundwater flow, just as Kenda was talking about. And so a lot of people think that it could have been a contribution from both. So not only precipitation from rain or snow, but also this groundwater. And as I mentioned, I think the leading hypothesis, also based on what we know from climate models, is that it's most likely snow that then later melted with heating events. But it's an ongoing question, and that's why it's exciting to go to another location to be able to test this hypothesis. So
it's awesome. Yeah, it makes me feel, a little happy for the future generation of explorers who are going to learn so much more. We have all these ongoing questions that kind of keep us curious and wanting to know. And this next question, in our audience right now, someone is watching named Philip Fox on Facebook, and Philip's young son, Lucas, is in 6th grade and also watching. And Lucas wants to know two things, and maybe all three of you could speak to it. One, Lucas wants to know, and again, it's in 6th grade, how to become an astrobiologist. And then maybe just for fun, Lucas also wants to know if humans will ever be able to visit exoplanets. And so those are two really good questions, Lucas, and thank you very much for those. Svet, I think I'll throw it to you first, if you don't mind.
I think all of us who come to astrobiology have followed a very unique and roundabout pathway. So I'd say follow your passion, just ask the questions, stay curious, and you never know what unique skills and interests of yours will end up being needed by the field of astrobiology, because it takes more than just the researchers, right? Astrobiology takes the communicators, the business managers, the folks thinking about ethics, of settling on other planets. It also takes the folks building the rovers and asking the scientific questions about landforms and deltas on Mars. So figure out which of those pathways you want to pursue, and don't be afraid to follow a slightly less traditional pathway to get there. As for exoplanets, I hope so. I don't think it'll be in our lifetimes, but I definitely am with you in hoping that one day we can make it there.
I love it. Kenda, how about you? What would you say to Lucas in 6th grade on how to become an astrobiologist and whether we'll ever travel to exoplanets?
Lucas, what I can say is I agree with Svet. There is so many. Astrobiology is truly an integrated scientist. It takes every different discipline of science to do astrobiology, because we need input for everybody, because it's such a big question. And that includes the engineers. And if we're going to go to an exoplanet, Lucas, we need young people like you to be interested in engineering, so you can develop the engines that'll get us to another solar system. So maybe engineering's in your future?
I love it. I love that you bring the expertise of engineering and astrobiology, and that could be part of Lucas's future, is engineering that for us. Francis, how about you? What should Lucas do to become an astrobiologist if that's the career he ends up choosing? And will we travel to exoplanets?
I would say something very similar as Kenda and Svet, like be true to yourself, don't compromise yourself, ask a lot of questions. I think a lot of people think that even though we're scientists, we don't ask questions, but that's literally our job, is to learn more. You don't only learn more by asking questions. And so, don't be scared to ask questions, and then try new things. And so as Kenda mentioned, and also Svet, it takes a lot of people with different disciplines to really bring astrobiology together, and figuring out how you fit into that picture only happens by trying different things and trying different hats. And so, take every opportunity that you can get to really constrain what you like and what you don't like, and keep asking questions, because that's ultimately what a scientist is, and what we do is ask good questions. and I don't think, and as far as exoplanets, I agree with Kenda. We need really good engineers. And so if you're really interested in getting to an exoplanet, figuring out the engineering to do that might be in your future.
I love it. Well, thank all three of you so much for joining us for Ask an Astrobiologist. For our audience right now watching, we had a lot more questions. I'm so sorry we couldn't get to all of them. My advice would be to reach out to Francis and Kenda and Svet online and ask them more questions and get involved in the conversation. Join us on SaganNet. Join us at NASA Astrobiology's Facebook page and on Twitter, and ask your questions there. And if you'd like to stay involved and in the loop on upcoming episodes of our show, upcoming opportunities for young scientists, early career researchers, and those interested in astrobiology, right now our producer-director, Mike Toyon, is going to put up a slide with information for how to join the NASA Astrobiology mailing list. We recently just changed the mailing list over to a new format, and so we're getting a lot more emails out there now, a lot more information of ways that you can be involved in all the things that we're doing. And then also, since we have, this incredible 3 missions getting to Mars in the next 3 weeks, I mean, it's so big, right? 3 new missions at Mars in one short window, including Perseverance landing on the 18th. If you'd like to know more about Perseverance and the mission, about Mars science, there's a huge amount of resources and information on events surrounding the Mars 2020 landing, surrounding Perseverance. If you visit go.nasa.gov/Mars 2020 Toolkit. That's go.nasa.gov/Mars 2020 Toolkit. You can find posters and stickers and mission patches, a Mars photo booth, and a bunch of guides on where to watch all of the different broadcasts, not only of the landing, but also leading up to landing day. NASA Astrobiology and NASA have so many things going on here in the next few weeks as we get ready for these missions. I know all 3 of our panelists are also super excited and probably going to be involved in a bunch of other events as well, as all of us get ready for this to happen. So one more time, Francis, Kenda, and Svet, thank you so much for joining us for Ask an Astrobiologist. All right, and then to our audience, thank you to all of you for joining. And until next time, remember, stay curious.